So when we talk about even and odd functions, what do we actually mean? We've heard of even and odd numbers. Like we know even numbers are 3, 4, 6, 8, etc. Odd numbers are 1, 3, 5, 7, etc. Now, odd functions and even functions, they don't really have anything to do with digits or with a number per se. When we refer to functions being odd or even, we're referring more so to symmetry of their graph. Okay, so odd functions, they a function is referred to as an odd function if its graph has point symmetry in the origin. Okay, now what does that mean? We know that the origin is in the middle of the Cartesian plane here, when x is 0 and y is 0. So what we sort of do is we draw like a sort of a line like here. Okay, think of this as like a symmetry line or a mirror line. And basically, this part of the graph here, or this part of the graph here, should reflect, it should reflect across this line. Again, that for it to be an odd function, right? So that's when you know a function is odd. If it has point symmetry in the origin. Okay, if it's reflecting across this line here, or across this line here. Okay, as long as it's reflecting across the origin, point symmetry across the origin, then it's an odd function. Okay, that's how we graphically figure out if a function is odd. Algebraically, we use this sort of notation here. So if f of minus x is equal to minus fx for all x in the domain, then a function is deemed odd. Now, this may seem a bit confusing and may seem a bit, it may seem a bit confusing, but we're going to go through some examples of this and how we actually figure that out, so it'll make some more sense later on. If you look at even functions, it's referring to symmetry, but here the function is called an even function if you have point symmetry across the y-axis. We've got our Cartesian plane again. We know our y-axis is this vertical line here. And we can see an example of this equation, y is equal to x squared. We can see that this graph has symmetry across this y-axis. If we take a reflection of this part of the graph across this line, we'll get this part of the graph here as a reflection. Okay, so that's again how we solve that graphically. Algebraically, we use this notation here. So if f of negative x is equal to f of x for all x in the domain, then a function is deemed even. Okay? So now we'll sort of go through some examples here, just so you guys know what that actually means. Okay? So we've already looked at function and function notation, and we basically know that this just means that we've got a function h of x, and that's equal to x squared plus 2x plus 1. Okay, now to verify whether this function is odd, even, or even, there's two ways you can go, right? You can try drawing up this graph, okay, and then you can see where the symmetry lies or if there's any symmetry. Or in this case, an easier way to do it is we use that algebraic notation that I showed you earlier. So what we do is we have h of x. So instead of x, we put in negative x. Okay, instead of x squared, we're going to have negative x squared plus 2 times negative x, and this stays the same as plus 1. Okay? And now we're going to try to solve this, or just sort of simplify it, okay? So negative x squared, we know that's just equal to x squared, because if you square a negative number, it becomes positive anyway, right? If you have negative 5 squared, that's the same as 5 squared. Or negative 5 squared is 25, 5 squared is also 25, okay? So negative x squared is equal to x squared, they're the same thing. 2 times negative x becomes minus 2x, okay? And the plus 1 stays the same. Now, this is a bit of a bad example to start because this function is actually neither odd or even. And that's because we cannot make this into negative hx or h of x, okay? What would negative h of x look like? So negative h of x would be if we somehow were able to get this whole thing and have a negative in the front. So if we had negative x squared minus 2x minus 1, that would make this an odd function. If we put in h of negative x and we just got this, the original function, h of x, then it would be an even function. Okay, but in this case, we've got a mixture of the two, right? We've got this negative 2x here instead of a positive 2x. And that's the only difference. So it's neither odd or even. Still a bit confusing. We're going to go through some more examples here. So then, yeah, we can determine graphically whether the following functions are even, odd, or neither. So remember, odd is when odd functions are, then just write it down somewhere. So we've got odd functions is point symmetry across the origin. So I'll just write 0 and 0 as the coordinates for the origin. And for even functions, we remember that the symmetry occurs across the y-axis. The y-axis. Okay, so let's have a look at this function here. If you drop a line across the origin, okay, we can see that this is not an odd function, right? Because if you take a reflection of this stuff across the origin, we don't have anything on the other side, okay? So therefore, it can't be an odd function. And if we test it whether it's an even function, that's when we're looking at the y-axis, right? And we could see this is a clean reflection across the y-axis. So therefore, this function is even. So I'm just going to write E for even. Okay. This function here, again, let's have a look at across the y-axis, and we can see that it's not a reflection across the y-axis, right? If it's a reflection across the y-axis, it would have been something like this. Okay, but it's not doing that, so then we just throw that out. Let's have a look if it's an odd function now. Okay. So if we again draw a line through here, we can see that this is a pretty accurate reflection across the origin here. Okay, so therefore we could say that this is an odd function. Okay, that's an odd function there. Now this one we can clearly see that it is neither reflecting across the y-axis, nor is it reflecting across the origin. So this one is neither. Okay. Okay, now let's go through another algebraic sort of expression. You can look at another function here. F of x is equal to 4x over x squared plus 4. And you have to determine whether this function is odd, even, or neither. And so we can do the same thing. We put in f of negative x. Okay, so that means that we have 4 times negative x over what? Negative x squared plus 4. Okay, now 4 times negative x is negative 4x. And as I said earlier, negative x squared is just x squared again. Okay, now here comes the interesting part, right? Now, when we put up f for negative x, we get this answer. Now, the only difference we have between this answer here, or this equation here, and this equation here, is that we've got a negative in front of the 4x there. Okay, now that negative is just in front of the numerator, sorry. So we can just take that out in front and put this equation in originally without the negative. Now, why do we do that? Is because if you look closely, this is the exact same as this, right? And we know that this is f of x. So basically, we've got negative f of x here, right? And that means that since f of negative x is equal to negative fx, we've got f of x is an odd function. Okay? All right, now we've got to verify algebraically whether this function is odd, even, or neither. Okay. Again, we'll do the same thing. Where f of x is equal to square root of 9 minus x squared, we can put in negative x. Instead of x squared, we have minus x squared. And as we've looked at in our previous 2 examples, minus x squared is the same thing as x squared. Okay, so when we put in f of negative x, our final equation just turns out to be that, which is the exact same as f of x, which means that f of negative x is equal to f of x, and therefore that means that f of x is an even function. Okay, so I hope that starts to make a little bit more sense now about how we do this algebraically. Um, you can, if you want, you can also look at the questions we're going through in this example and try practicing drawing them graphically, or use an online software to draw up that graph and see graphically how you can tell whether they're odd or even or neither.